Section 10.1, Sequences. The goal of this section is to extend calculus techniques to infinite sequences and series, so let's begin by defining some terms. Definition. A sequence A sub n, which we write like this, is an ordered list of numbers defined by a function f on a set of sequential integers. It's probably helpful just to look at an example. So let's take the sequence 2 to the n, where n goes from 1 to 6. So a couple of definitions here, or little bits of jargon, is we call this 2 to the n the general term. It tells us the general pattern of what all the terms in the sequence are going to look like. This is called the indexing variable, or the index. This is the starting value of the index. This is the stopping value of the index. So think of this as the template or pattern, 2 to the n, and then we're just going to substitute in n equals 1, followed by n equals 2, followed by n equals 3, and we're going to count by ones starting here, ending here, and we're going to generate an ordered list of numbers. 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth. The order definitely matters here. These individual terms are called the terms of the sequence, and this is called the general term. Now, if you think of this, this is just a function that is taking the integers 1, 2, 3, 4, 5, and 6 as inputs and assigning them to these outputs. So that generates a function. You could think of this, if you draw this as a table, that we have our n values here, we have our corresponding a sub n values here, and then this creates a bunch of ordered pairs, which we can plot. This axis would be n, this axis would be a sub n. We could plot those ordered pairs, and we get this discrete plot of points. And this would be the graphical representation for this sequence. Sometimes we're given the terms and we must construct the formula for the an, or the template for the an. So imagine you were given this list of terms. Now notice in our last example we only had finitely many terms. It was a finite sequence. It terminated after 6 terms. But here this pattern, 1, minus 3, 5, minus 7, 9, minus 11, 13, and so on. The dot 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 here is very, very important. It tells us that the pattern continues infinitely, and this sequence has infinitely many terms in it. So here, if you think about this and reflect on this, what's really happening, we see a couple of things. Here we're just counting the odd integers. If you ignore the minus signs here for a second, 1, 3, 5, 7, 9, 11, 13. But the signs are alternating, so we need, whatever formula we come up with, needs to incorporate the fact that the signs alternate, but then also that we're counting the odd numbers. So if you think about that, writing 2n minus 1, that's a pattern that's going to guarantee that we generate these odd numbers. And then if we write minus 1 to the n plus 1 power in front of it, this is just a term that is alternating between a positive 1 and a negative 1, a positive 1 and a negative 1, as we iterate here on the indexing variable n. And we can just check this. We can write this down, and truthfully, when you go to do these, you just write down a pattern, and then you want to check it. You see if it's correct, and if it's not, then you adjust. So here I just wrote down the pattern a sub n, and now we can check it. We just check to see if this is indeed the term that we get when we let n be 1 in this pattern. When we substitute an n equals 1 into this pattern, it's exactly like substituting an n equals 1 into a function. Everywhere we see an n, we're going to put a 1. And then when the arithmetic is finished here, we get a 1, which is our first term. When we substitute the next index, n equals 2, everywhere we see an n in the pattern, when the arithmetic is done, we get a minus 3, which is the second term. Similarly, when n is 3, we get a3 is 5, and we can keep doing this for all of these terms. So this verifies that this is indeed the template or the function or the pattern or the general term for this sequence of terms. We can also graph this an. So here, again, we can generate a table starting at n equals 1, and we'll just generate, say, the first 7 terms. And then we calculate the an's, and we see we get 1, 3, minus 3, 5, minus 7, 9, minus 11, and so on. And I'm putting the dot 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 here to show you that this would go on forever. Of course, when I'm actually doing this, I have to stop after some finite number of numbers. But here, this pattern is going to go on forever. This has an interesting discrete graph, if you will. Again, this is the n-axis, this is the a sub n axis, and if we plot these discrete points, we see that we get this alternating series because the terms are flip-flopping between positive and negative. Example 3. Consider the sequence 3, 3 over 10, 3 over 100, 3 over 1,000, 3 over 10,000, and so on. The pattern again is continuing forever. Now if you just cover this up and you try to figure out the general term an here, it definitely looks like it has a 3 in the numerator. It looks like we're counting up on powers of 10, 10 to the first, 10 to the second, 10 to the third, 10 to the fourth. This in the denominator is a 1, which is the same as 10 to the 0. And so we could postulate the general term to be an equals 3 over 10 to the n minus 1, where n starts at 1 and just continues 1, 2, 3, dot, dot, dot. And you can check this. If you plug in n equals 1, you get 3 over 10 to the 1 minus 1. That's 3 over 10 to the 0. That's just 3. If you plug in n equals 2, you get 3 over 10 to the first. If you plug in n equals 3, you get 3 over 10 to the second. So this pattern, this general term is correct for this given sequence. But notice you could also write it a different way. You could also write this as 3 over 10 to the n, where n starts at 0 and then goes to 1, 2, and so on. And the moral of the story here, and you can check this one, the moral of the story here is that there are multiple correct ways to represent a sub n with different functions for n. So this representation is not unique. Normally we want to pick a representation where the index starts at a 0 or a 1. Sometimes it makes a difference depending on other factors that are in play, but these are both perfectly acceptable general terms. Notice also that you can't talk about the general term without also talking about the indexing range, where it starts and where it stops. So to just say that this is a sub n or this is a sub n without including this would not provide sufficient information. Once again, if we take this formulation and we plot this, we can generate the table of the a sub n's, and then we can generate the graph. And we can see that the terms are getting smaller and smaller in magnitude as we progress through the sequence, and we can see that in the graph as well. So our main goal in this section is to study not just sequences, but we want to study their limits as n goes to infinity. So we need to talk about what it means for a sequence to converge or to diverge, what it means for it to have a limit or not have a limit. So here's a definition, and these are just taken from the textbook. We say that the sequence a sub n converges to a limit L, and we write the limit as n goes to infinity of a sub n is L, or a sub n goes to L, if for every positive epsilon there is some number m such that the absolute value of the difference between a sub n and L is less than epsilon whenever n is greater than m. Now that's quite a mouthful, so we need to break that down. To go on just a little bit further, if no limit exists, so if the sequence does not settle down to a limit L, we say that the sequence diverges. On the other hand, if the sequence doesn't settle down because it's becoming unbounded, we say that the sequence, it's okay to say that the sequence diverges, but a little more precisely, we say that it diverges to infinity. Now, the idea of this definition is that, think back to those plots that we had. If you were to view or visualize the graph, the discrete graph of a sequence, if it's going to settle down to a limit L, then what has to happen, if it is going to have a limit L, what has to happen is, if you go far enough out in the sequence, the terms of the sequence, so these dots, need to get within epsilon units of L, either above or below, for any epsilon that you pick. You might pick epsilon to be 10 to the minus 2 or 10 to the minus 5 or 10 to the minus 10, and it has to get arbitrarily close to L if we go sufficiently far out, and that's what this is saying. If you can pick any positive epsilon you want to, you can dare the terms of your sequence to get within epsilon of L, that's what this is saying, either above or below, and it's not guaranteed to always happen, but it's guaranteed if this has a limit of L, it's guaranteed to happen if you go sufficiently far out in the sequence. So I think that this diagram is very informative. Now, how are we going to compute sequences, or compute limits of sequences? We could use this definition, but we're going to develop some more efficient tools, And one of the most commonly used tools to calculate the limit of a sequence is using this theorem. So the idea is, if you think of your sequence as defining a function, then the limit of your sequence and the limit of the associated function will be the same, assuming that this limit exists. Let's show you some practical examples. So consider here the limit as n goes to infinity of 3 over 10 to the n minus 1. So here our an, which we can think of as f of n, is the function 3 over 10 to the n minus 1. That says our function f of x is 3 over 10 to the x minus 1. So we know that this is an exponential term in the denominator. The numerator is constant, so the numerator is staying fixed at 3. But as x gets really, really large and positive, the denominator is becoming unbounded. It's going to infinity. So this entire quotient is going to 0. So this limit is 0. Now, I'm not saying that you necessarily have to formally write this out. You may say I can look at that, and I can just think of what you're really doing is you're thinking of the function 10 to the n minus 1 in the denominator, and you're saying that as n goes to infinity, this term in the denominator goes to infinity, and so this quotient goes to 0. That's exactly what this theorem 1 is allowing us to do. We calculate limits of sequences very similarly, almost identically, to the way we calculated limits of functions in Calculus 1. As a second example, look at the limit as n goes to infinity of n plus ln of n over n squared. Now, if you stare at that, here's our sequence. We're taking the limit of our sequence, and here our an is fn, f of n, which is n plus ln of n over n squared. So our function that we're thinking about is x plus ln of x over x squared. But there's no harm in just thinking of it as this. And now we look at this as n goes to infinity. This numerator is going to infinity, and the denominator is going to infinity. So this is an infinity over infinity indeterminate form. We can use L'Hopital's rule. L'Hopital's rule just says we take this limit is the same as the limit as n goes to infinity of, take the derivative of the numerator, and separately take the derivative of the denominator. And we hope that this helps resolve our indeterminate form. We see that this form here in blue is no longer an indeterminate form because as n goes to infinity, this term goes to 0. And now we have a 1 in the numerator and a denominator that is becoming unbounded. It's going to infinity. So this quotient is going to 0. So we would say that this sequence converges, and it converges to 0. As a third example, suppose we had the limit as n goes to infinity of e to the n over n. This is again an infinity over infinity indeterminate form. We can play the same game that we've played before, but using L'Hopital's rule, this is the same as the limit as n goes to infinity of the derivative of the top, which is e to the n, over the derivative of the bottom, which is 1. This is no longer an indeterminate form. As n goes to infinity, this is going to infinity. So this sequence diverges, or diverges to infinity. I won't make a big deal about the difference between those two descriptors. We would say that this sequence diverges. Now, a couple of things we just need to enter into the official record, and those are the algebraic properties that we have when dealing with sequences of limits. So suppose we have two sequences. They're individually convergent. Let's say that this converges to a limit of L, this converges to a limit of M. Then what it says is if you have the limit of a sum or a difference of these two, you can split the limit up over the addition or subtraction, and you can take the limit of the pieces. So limits of sequences behave very nicely with respect to addition and subtraction. They also behave nicely. You can split this action up over multiplication. You can split this action up over division, assuming that the denominator is not 0. And it plays nicely with scalar multiplication, because if you have a constant times a sub n, you can just pull the constant out and take the limit of the a sub n. Now these limits do have to exist. These have to be convergent sequences, but these can make our life a lot easier when we are calculating limits of sequences. The next category of sequences we want to look at are the so-called geometric sequences. So as a definition, a geometric sequence is a sequence of the form where the a sub n, the general term, looks like some number c times some number r raised to the n. So this is a very, very important class of sequences. We want to make sure that we're familiar with them. Here, c and r are non-zero constants, act like they're numbers that we know. The constant r here is called the geometric ratio. since if you take any two consecutive terms in this sequence, they will always have a ratio of r. So just take the k plus first term and the kth term. The k plus first term would look like c r to the k plus 1. The kth term would look like c r to the k. Notice the c's cancel. You can cancel k powers of r here with k powers of r here to just get a leftover r. And this is true. It doesn't matter if you do a3 over a2 or a7 over a6 or a99 over a98. It doesn't matter. You'll always get a common ratio of r, and this is called the geometric ratio. So as an example, if you take a sub n to be 2 to the n, then this is certainly a geometric ratio. The understood one that's on the front is your c, and the r here is 2. The geometric ratio is 2. On the other hand, from our previous example, if you had a sub n is 3 over 10 to the n minus 1, this doesn't match our template for a geometric sequence right now. So sometimes you have to algebraically rearrange things to make them match. Notice this is an n minus 1 power and this is an nth power. So we'll just do a little algebraic gymnastics here. We will take this, multiply the top and the bottom by 10. This becomes a 30, and in the denominator we get a 10 to the first times a 10 to the n minus 1. That gives us a 10 to the n. And if we just rewrite this as 30 times 1 over 10 all to the n, notice this now matches our required template. It looks like a constant times an r raised to the n. It's very important that we match this template exactly. So this is a geometric sequence. The c here is 30 and the r is 1/10. Next, let's talk about convergence and divergence of geometric sequences. We want to catalog these because they're going to be very useful to us going forward for the rest of Chapter 10. So let's consider a geometric sequence. For right now, let's take the geometric ratio to be a positive number. Remember, it cannot be 0, but it could be negative. And let's just look at this first case where the r is positive. We want to break this into 3 subcases. Either r is strictly between 0 and 1, r is exactly 1, or r is greater than 1. Well, notice if r is between 0 and 1, that if we take the limit of the a(n)s as n goes to infinity, that's the same as taking the limit of this as n goes to infinity. And if you stare at this, since r is a fixed number between 0 and 1, we're raising a number between 0 and 1 to a higher and higher and higher power. That's going to make this term go to 0, which is going to cause the entire limit to go to 0. So this is always going to converge. This geometric sequence is always going to converge when your geometric ratio is between 0 and 1. On the other hand, if r is equal to 1, then we know we can just put a 1 in where we see an r, and 1 to the n is just 1. And so we get this limit. It's just the limit of c times 1, which is just c. That's a constant. That definitely converges. So when r is equal to 1, we also get convergence of the geometric sequence. Finally, if r is greater than 1, and we play this same game, we get to the same step here, but now the r, the geometric ratio, is a fixed number that's greater than 1. So think of this as like a 2 to the n, or a 10 to the n, or a 100 to the n. As n gets bigger and bigger, this term is going to infinity because the r is greater than 1. That makes this entire limit go to infinity, and that says that in this case, the geometric sequence goes to infinity, and so it diverges. So now we know when we have a positive geometric ratio, we know exactly where it converges, the geometric sequence converges, and we know exactly for what r values the geometric sequence diverges. We can play exactly the same game when we have a geometric sequence with a negative geometric ratio, because that is certainly allowed. Again, let's break it down into 3 cases. Either our r is between minus 1 and 0, in which case, again, because the r is between minus 1 and 0, the limit goes to 0. The limit of the geometric sequence is 0, and so the sequence converges. Or the r is exactly minus 1, in which case when we put a minus 1 in for r, this becomes a c times a minus 1 to the n. Notice the difference that this minus 1 makes. This is now, when we pull the c out, this is now a sequence, right? This part of the sequence is flip-flopping between a positive 1 and a negative 1, a positive 1 and a negative 1. So if you go back to that epsilon definition, this limit does not exist, and therefore the sequence diverges. Finally, if r is less than minus 1, then the limit of our geometric sequence, again, we have a geometric ratio that is larger than minus 1. So when we raise it to a bigger and bigger power, this is becoming unbounded. It's actually flip-flopping signs also, but in magnitude it's becoming unbounded. This limit does not exist, so the geometric sequence diverges. To summarize all 6 parts that we did in these 2 cases, the grand conclusion here is that if we have a geometric sequence and we know its geometric ratio, which we will always be able to determine, this sequence diverges if r is less than or equal to minus 1. It converges if r is between minus 1 and 1 but including 1. And it diverges if r is strictly greater than 1. So this is definitely something that we want to have in our repertoire. This will come in very handy for geometric, knowing when geometric sequences converge or diverge. We need a few more tools to be able to calculate a variety of limits of sequences. Another tool is the squeeze theorem for sequences, stated here. It just says that if you have 3 sequences, an, bn, and cn, and the an is squeezed between the bn's and the cn's, if the bn's are limiting to L and the cn's are limiting to L, then the an's have to be limiting to L also. So they're squeezed in between the bn's and the cn's. Here's a classic example of how you can use the squeeze theorem for sequences. Suppose we wanted to find the limit as n goes to infinity of e to the minus 0.3n times sine n. Now if you notice, just individually, as n goes to infinity, this term's going to 0. But this term does not exist. It just oscillates between minus 1 and 1. So it's not a L'Hopital's rule type problem. This is just a does not exist. And so now what happens when you have this 0 times this does not exist? Does the limit exist? Does it not exist? How do we find out? Well, let's just take our given function and let's be clever and use the fact that sine n is trapped between minus 1 and 1. So if sine n is trapped between minus 1 and 1, and we multiply all 3 parts of this inequality by e to the minus 0.3 times n, then we have a set of inequalities. And here we just have this function is squeezed between these 2 functions. Now look at what's true about these 2 functions. As n goes to infinity, this is a decaying exponential function. This is going to 0 as n goes to infinity. This is a decaying exponential function, just with them being multiplied by minus 1. As n goes to infinity, this is going to 0. And so by the squeeze theorem, since this is going to 0 and this is going to 0, by the squeeze theorem, this must be going to 0 also. And so this is a very useful tool for definitively determining the limit of that sequence. Now, if we were to actually plot the table here, generate the table of the terms, this is what we get. This is the graph. Graphically, you can see the sequence, the graph of the sequence settling down to 0. I'm not saying that this is a proof at all. This is the proof. But this is just numerical and visual evidence to show as n gets larger and larger that these are settling down to 0. Another theorem is that if f is a continuous function and you know that the limit of the sequence an is L, then the limit of f of an is the same as the limit f of the limit of the an's, which is the same as f of L. The way to think about this theorem is you can push the action of the limit inside of a continuous function. And so let me show you what I mean with a specific example. Suppose you want to find the limit as n goes to infinity of the square root of 1 plus 2n over 1 plus 3n. Now, if we were to erase this square root, we know how to take the limit of this. Either through L'Hopital's rule or things that we've learned in algebra, we see that this limit is going to 2/3. If you just want to think L'Hopital's rule, that in here this is an infinity over infinity indeterminate form. When we take the derivative of this, we get a 2. When we take the derivative of this, we get a 3. So this is limiting to 2/3. Well, we got this square root here. And so how do we handle that? Well, since the square root function is a continuous function, we can take the limit of the square root of this function and push the limit inside the square root because this is a continuous function. So it says that limits and continuous functions can be interchanged. So if we interchange the order here and we do the square root of the limit, that's what this theorem allows us to do. Now we work just on the inside of the square root, and we get the limit as n goes to infinity of 1 plus 2n over 1 plus 3n. We already argued that this goes to 2/3, and voila, we are done. Once again, graphically, we can look at our sequence. an is the square root of 1 plus 2n over 1 plus 3n. Here's a table with the terms. This is not a proof, but if you look at this, this looks like it's very slowly converging. The graph looks like it is converging. It's settling down. It turns out that what we did analytically is we came up with its limit is the square root of 2/3. The square root of 2/3 is approximately 0.816, and this is where its graph is settling down to.